All right, everybody, this is lecture 5. As you all are aware, we have some more bad weather coming, and so I thought I would pre-record this lecture in advance, just in case Marshall decides to close or delay tomorrow. I kind of think they're going to go ahead and do so. Just a quick announcement. Attendance grades are up to date. What I'm going to do for Friday's lecture, or tomorrow's lecture, I should say, because I'm recording this the day before, is I'm just going to count everybody present, independent of whether they make it or not because of the weather. And so I'll just count everybody present to make that easy. Homework 1.2 should be graded, and the solution should be posted by the time this lecture goes live. 2.1 is going to be due at the time the lecture goes live, and then 2.2 will be assigned and due Monday. It's only one problem, and so it's a little bit longer than the two. So there were 2 problems on the last assignment. This next assignment only has 1 problem. It's a little bit longer than either one of those, but I actually think it's kind of a short assignment because once you start to see the pattern, it's pretty easy to see what's going on with it. But that'll become clear as we start to navigate through the topic today, which is on staggered bolt paths. And we talked about this a little bit in class on Wednesday. We didn't quite get a chance to finish it or to really delve into it in detail, so that's kind of what we're going to do today. So with that, let me go ahead and pull up the lecture notes. Let's see. Lecture 5. Okay. All right. So let's just make sure that we recap where we left off last time. Last time we were looking at computing net area. So just a little bit of a larger picture. When we're looking at tension members, we have so far we have 2 limit states that we've discussed: yielding in the gross section and then fracture in the net section. And so to compute the capacity according to yielding in the gross section, it's just the yield stress times the gross area. And for fracture in the net section, it's the tensile stress times the net area. More specifically, the net area adjusted by this shear lag factor U. So really the first few lectures are focused on computing net area and computing U. We haven't talked about U yet. We're going to talk about that later. But for now, we've been focusing on net area. Now, for net area, we take the gross area and we subtract the area loss due to the presence of bolts. And up until now, we've only looked at grid-like or parallel bolt patterns where everything's in one nice rectangular grid. And so when you cut a section and look at the net area, the net area is just, in those cases, is just going to equal the gross area minus however many holes you're subtracting. And so the sum of all the holes that you're removing. And those holes are the diameter of the hole times the thickness. And remember, we add 1/8 of an inch to the diameter of the bolt to get the effective hole diameter. And the reason why it's an 1/8 is because we add a 1/16 twice. 1/16 for erection tolerance. So we actually drill the hole 1/16 of an inch larger. And then another 1/16 on top of that to account for damaged material. Now, the problem with that formula is when we deal with situations like this. So the formula that I just showed on the previous slide works very well for the upper case where you have parallel or grid-like arrangements of bolts. But when the bolt arrangements are staggered, the formula doesn't work very well because if you look at your net section, for a grid-like situation, we're just going to have this, right? But if we're just talking about the lead line, and I'm going to get to the lead line here in a bit, and before I do that, I'm actually going to make my camera a little smaller so all the text shows up there on the slides. But if we look at the net section, let's say along a staggered arrangement, the section, let me go back. The section might actually look something like this. It might go down, over, down, over, down, over. And so the actual failure path is going to be different for staggered arrangements than it is for parallel arrangements, whereas parallel arrangements is just perpendicular. Now, and we mentioned this in the last class, but just to reiterate, a natural question is, why would you even do this? Why would you waste your time with arranging bolts in a staggered fashion in the first place? And the reason is to increase the net area. So it's sort of easy to see that if you were just think of this in terms of length. Okay, let me redraw these just so that the lines are through the members. So maybe something like that, and then maybe something like that. So imagine just taking a piece of yarn and laying it along these two red lines, the one up top and the one below. It's pretty easy to see that the piece of yarn for the bottom, the staggered arrangement, is longer, okay? So if that failure path is longer, that results in a larger net area. And if we increase the net area, we increase the capacity. So we're able to use the same member and get more strength out of it. Or more specifically, we might be able to use a smaller member if we stagger our bolt arrangement. So there's multiple reasons why you would do it. So it's not done just spuriously. There are reasons for it. But there are some complications whenever you deal with staggered bolt arrangements. The first is, how do we actually account for the area increasing? I mean, so we have the gross area minus the area lost due to the presence of bolts, but then plus what? I mean, the area is increasing, so what are we adding? We've got to be adding something. What are we adding? And so the spoiler alert, those are going to be called stagger factors, and we'll talk about that here in a second. But then the other question is, how do we account for multiple failure paths? And I'll show you what that means here in the next slide. But what I want to focus on this slide is that whenever we investigate staggered connections, we only investigate failure along the lead line of bolts. And the lead line of bolts is what you see here. The reason for that is because whenever we look at a potential stagger path, we only look at ones that leave all the bolts intact. We can actually do the math for if we fracture one, but the resulting net area ends up being so much larger that you could pretty much neglect that in just about any case. Now, the lead line, and I've got a single member with two different connection regions here. The lead line are all of the bolts that are hovered around the inside of the connection. And so the way I usually like to describe the lead line is, imagine if you were standing on this tension member, something like that, and you had a flashlight in your hands. That's my best flashlight. And you shone a flashlight, and that flashlight just, sort of shone a beam of light, like this. What bolts would it hit? And it would hit, this one, this one, this one, this one, this one. All of the other bolts would sort of be in the shade, as it were, if that makes any sense. These white bolts here would sort of be in the shadow of the bolts that are in front. And so we call that the lead line. And you're going to see here in a second why the lead line is what we consider. Okay, so let's actually take a look at that. Okay, I am going to move my camera up here so that we can see all these letters. Maybe I'll make that a little bigger. Okay, so here I've got a given staggered connection. Okay, and I've got some letters here on the slide, and so these letters are going to help me name some potential failure paths. Okay, and you'll see what I mean here in a second. So what we're going to try and do is identify all the potential ways that a net area section could fail. And this is one of the I don't want to say the downsides of a staggered connection, but it is one of the realities of it, that there are multiple potential ways that the segment can fail. And so we have to investigate all of them. All right, so let me give you kind of an idea. Okay, and I'll do one for you. I'll start you off with one. Okay, so one potential failure path is, I'm going to call, my pen doesn't like me. It's this right here. BDG. I don't think it's the pen. I think it's where I'm touching the touch screen. It's wanting to go to the next slide. Okay, so path BDG is a potential failure path. Okay, so let me draw that path. Okay, so I propose that what could happen is the member could fracture along this path. And so think about what the net area would look like. The net area would look like the gross area minus, let's say, one bolt hole. Okay. Now, one natural question that students ask at this point is BDG. I'm saying BDG is a potential failure path. Okay. What about ADG? Couldn't the member fracture this way? And I'm going to say the answer is no. Okay, and the reason why I'm saying that is, imagine if you're holding let's just say you're holding a piece of taffy, okay? And you take that piece of taffy and you yank it, and the taffy snaps in half. The taffy's not really going to snap at some sort of diagonal angle. It's going to fail along the path of least resistance, right? So think if capacity is a function of area, okay, and I take a piece of steel, let's just say I take a piece of steel and I yank on it, it's not really going to fail. Oh, my camera's in the way. Move that over again. So if I have a piece of steel and I yank on it, it's not really going to fail at a section like this. It's not going to do that, okay? Instead, it's going to fail along the path with the smallest area. I mean, if I have a piece of steel and I cut through it like this, that surface that I'm cutting through is going to have a bigger area than if I cut like this. The area through that member is the smallest through that perpendicular section. So that's why whenever I'm identifying these failure paths down below, all of the failure paths are going to be perpendicular to the axis of the member other than between bolt holes, okay? Because we could fracture between bolt holes. And so let me kind of show you what I mean. So one additional potential failure path is B, D, E, F. That's a potential failure path. So all of the lines are perpendicular between bolt hole and edge of plate. The only one that's diagonal is from bolt hole to bolt hole, because we could fracture along that line. That's potential option. So one potential option is line B, D, E, F. So B, D, E, F. Now, another option, and I'm going to assume for the sake of discussion that this plate is entirely symmetric. So imagine, you know, folding the plate right along that line, and I get the same connection on either side. So if B, D, E, F is a potential failure path, then so is A, C, D, G. Again, perpendicular lines except for between bolts. Now, if everything's symmetric, this path and this path, this A, C, D, G, and B, D, E, F, they're pretty much the same path. There's nothing really different. And why am I saying that? Both of the paths have two bolts that they're going through, and then there is a single diagonal path, a single diagonal region. Two bolt holes, one diagonal with both paths. So I'm going to say that numerically they're going to be the same. Okay. Now the other potential failure path is A, C, D, E, G. Okay. Now, how am I picking these paths? Well, first off, what I'm doing is I'm only going through paths that consider the lead line of bolts. Okay. How am I knowing the lead line? So I'm actually sort of paying attention to this lead line, or this brake line right here. Remember, the brake line is where the main body of the member is. So whenever you see a brake line, think that's where the person with the flashlight is shining towards the connection. And so what bolts are they going to see? They're going to see that one, and that one. Okay, so that's where the naming convention comes from. Now, every single one of these paths, if I separated the member along those paths, it would leave all of the bolts intact. You know, for example, if I fractured here, fractured here, fractured here, fractured here, I could take that right piece of plate and sort of take it off, and all of the bolts would remain intact. So the big question to ask is, what about A, C, E, F? What about this path? Okay, if I were to fracture along here, so again, taking a samurai sword or lightsaber through that line, okay, I would separate the plate in half. Like that there's no arguing there. The plate would separate into two pieces, not in half. It would separate into two pieces. But I wouldn't be able to remove that right piece. I wouldn't be able to pick it up and take it with me because it's still being pinned down by this bolt D over here on the right. Like, that doesn't really happen if I fracture out here. Like, if I fracture out here, the idea is that I could pick up that plate on the right and take it with me. I can't really do that with ACEF. With ACEF, that's not going to happen. In other words, to completely separate the member, you know, imagine this member is holding people up, and for those people to quote unquote fall down, for them to be in danger, not only would you have to fracture through the plate, but you also would have to fracture bolt, right? So this failure path would not be a conservative pick. It would not be a worst case scenario because you would have to fracture through the member and the bolt in order to jeopardize safety. Whereas the other pass, all you got to do is fail through the plate in order to jeopardize safety. So that's why we only consider along the lead line. So we would not consider ACEF as a potential option. Now, how do we account for diagonal paths, or how do we account for these staggered paths? Well, for every diagonal region, we incorporate a stagger factor. Okay, so we add a stagger factor to each diagonal path to account for the increase in net area. And so this is what I mentioned earlier, that we take the gross area minus the area loss due to the presence of bolts. But then I said we're adding something. We have to add something for the increase in net area. And so what we're adding is a stagger factor for every diagonal path. Now, the way that we compute a stagger factor is we compute S squared over 4G times the thickness. Now, here's the code reference. One thing I'll mention about the code reference is that if you actually open this section of the code up and read this, you're actually going to get a different answer, because the code doesn't say S squared over 4G times the thickness. It just says S squared over 4G. Because the way the code's written, it's just saying, here's the amount that you have to add for each path. But then you have to multiply that length times the thickness in order to get an area. So that's why I put the thickness here, because you're going to have to multiply that out anyways. Now, the notation, the way the notation's working, S is the longitudinal spacing and G is the transverse spacing. And so what I mean by that is S is parallel to the application of load and G is perpendicular to the application of load. So you got to make sure that you're using the right terminology here when you apply stagger factors. Don't worry, we're going to have an example on this here in a second. Now, one thing I will mention is whenever you're computing stagger factors, this is sometimes an area of confusion with students, and so I want to make sure that it's clear. So I have a connection here. No, I don't think this connection would be very realistic in the real world, but I'm using it just to illustrate a point. So let's say I have a connection and I'm trying to investigate, let's say, this failure path. Okay, let's just say I'm trying to investigate that failure path. And so I would say that the gross or the net area for that path would be the gross area minus, okay, 1, 2, 3, 4, 5 bolts. So 5 bolts plus, now here's the kicker. The kicker is that I would say 4 stagger factors. Okay, now those stagger factors, again, S squared G over 4G, or S squared T over 4G, what I would do is I would compute a stagger factor for this path. So that S, that G. And then a stagger factor for this, that S, that G. And then repeat that. So I would use 4 individual stagger factors. What I would not do is one big old stagger factor for the whole thing. And the reason is that the algebra doesn't work that way, because you're taking S squared over 4G. So you can't take one big diagonal path and compute one stagger factor and get the same numerical value as 4 individual ones. You have to compute each one separately. Okay, so you would use 4 separate stagger factors. So what is a more complete expression for net area? This is going to be our real expression for net area. So we've been building for this since the last lecture, and now I can sort of just say, hey, here it is. So our expression for net area is to take the gross area minus the sum of all of the bolt holes, which is the diameter times the thickness. Again, diameter is the bolt diameter plus 1/8 of an inch, plus any stagger factors. And the stagger factors are S squared T over 4G. Now, one of the things I put here on this slide is that that's our expression for bolted connections. What about welded connections? Well, the net area for most welded connections is just equal to the gross area. And I say that this is because no material is removed from the connection. I guess I should more specifically state that's usually no material is removed from the connection, especially for the welds that we deal with in most structural steel applications like fillet welds. You're not really removing material. You're just taking a piece of steel, lapping it on, and stitching that together with some fillet welds. You're not removing any plate from that. There are plug welds or slot welds or things like that where, you know, you could remove them, but those aren't as common as just a regular old fillet weld. So just want to mention that for clarity. Okay. So to clarify what we're doing here, I want to go through the following example. So we're going to compute the net area for this plate, this connection. The plate is 1 inch thick. We're using 3/4 inch diameter bolts, and I've got a series of dimensions here. A couple things that I'll point out. One of the things that you'll see in these dimensions is this term typical. So actually, let me pull up the notebook here because we're at a point where I can go ahead and just start with the notebook here. Okay. So whenever you see the term typical, that just means that all of these are essentially going to be 1/2 inch or 1.5 inches. So for example, like, here to here is 1.5, here to here, that's 1.5, that's 1.5, and so on and so forth. And so you'll see typical a lot in structural engineering schematics, just so that you don't have to keep repeating the dimensions over and over again. When it's needed to be explicitly stated, you will, and whatnot. Now, what we're going to do with this problem is we have to identify, let me make my camera just a little bit smaller so I can see that dimension. We have to identify the gross area, and then we have to identify our bolt parameters. But really the big thing is we need to identify all of the potential possible failure paths. Okay, so I'm actually going to go ahead and put some naming on here just to make sure that we're all clear with that. So let's do A, B, let's name this C, D, E, F, and G. Okay, just so we have all of our potential paths laid out. Okay, so let's see if we can draw some of these out. So the first one I'm going to assume is going to be a path is this one right here. Okay, so we'll call that path ADF. So path 1, we'll call that ADF. Okay, what about path 2? Let's make that green. So path 2, I'll call path 2 B, C, D, F. I'll just sort of draw it like that. So 2 is B, C, D, F. Now, before I move on, one of the things to mention is what's going on here with these dimensions. It's all symmetric. Like we have 2.5, 3.5, 3.5, 2.5. So if I folded right through the middle, this is symmetric, which is, again, pretty common in applications. We try and exploit symmetry whenever we can. Just because we're staggering bolts don't mean we have to make it unnecessarily complicated. Now, that's not to say that you will always have staggered connections that are symmetric. There are actually real examples where that isn't the case, and a good example of that is when you have stagger across angle legs. We're actually going to look at that a little bit later, but I just mentioned that just to say that whenever we exploit symmetry, or whenever we have symmetry, and we can exploit it, we usually do. Now, my overarching point, though, is if BCDF is a path, then what's the other path that corresponds to that? It's A, D, E, G. Okay, and then finally, I keep hopping my camera around. I'm sorry, but I don't want that to get crammed. All right. Finally, we'll do this in black. My last path that I see as a potential failure is B, C, D, E, G. And again, those are all the potential failure paths that keep the bolts intact. And again, the two sort of thoughts I want you to have in terms of whether or not a path is along the lead line is, one, that person standing on the member with a flashlight, what elements are they going to see? And then two, if you were to take a pair of scissors and then cut the plate along that path that you defined, could you pick up the rest of the member and take it with you? Okay, that's the kicker. And if there's any bolts that are still pinning it down and preventing you from moving it, it's not on the lead line. Okay, so let's go through a couple things. First thing I want to do before I actually move on is let's look at this right here. I actually want to look at this dimension. So we have 2.5 and 3.5. So 2.5 plus 3.5 is 6. Okay, so times 2 is 12. So this dimension is 12 inches. Okay, and so if that dimension is 12 inches and the plate is 1 inch thick, we know that the gross area is, boom, right there. Okay, so before we move on, let's just have that down. The other thing I want to mention is the bolt diameter. So we know that this, let me move this up a little bit. We know that that is 3/4 of an inch. So therefore, we know that. Or I should rename that, should I? D sub E. D sub E is 7/8 of an inch. Okay, so we've got some stuff figured out. Now let's see if we can identify a few other parameters before we move on. Now, let's go ahead. Let's do this stagger factor. Let's do that. So let's put this stagger factor over here. Now, I'm going to put my expression for a stagger factor right here just so we can have it. We can have that sort of handy. So our stagger factor is S squared T over 4G. T is easy. T is 1 inch. Okay, so what's S and what's G? S is the longitudinal spacing along the direction of loading. So we're taking this element and we're loading it like this. This is how we're yanking on it. Okay, so if we're yanking on it this way, then the stagger is the longitudinal direction. In other words, stagger is along the direction of loading. So the S value in this case is going to be the 1.5, that typical dimension there at the bottom. Now, what about the gauge spacing? The gauge spacing is transverse. It is this direction, perpendicular. But the crystal, or the salient point is that the gauge spacing is from bolt to bolt along that diagonal path. And so in this case, it's 3.5, okay, because we're talking about that dimension right there, okay? So if that's the case, then therefore my stagger factor is this. Okay. All right, so I didn't bring my notebook home with me, so we're doing this one on the fly. Okay, so 1.5 squared over 4 times 3.5 is 0.161. We'll do 3 decimal places, and we'll say that that's square inches. Okay. All right, so let's also be clear on one final thing here. So hole area. The hole area, so what do we have? We have the diameter of the hole as 7/8 of an inch, and we have the thickness as 1 inch. So we'll call it area hole is the diameter times the thickness, which is just that, 0.875 square inches. I can make that E there a little bit more clear. Okay, there's a reason I'm doing that, that I'm computing all these parameters separately, because I'm a big fan of making the math as easy as possible, and I like to do things in tables. And so what I mean by that is our net area expression. So here, let's do it like this. So let's put net area. Okay, so our net area expression says that the net area is the gross area minus the sum of our hole diameters, which this is just the area of the hole, plus the sum of all stagger factors. Like, that's our net area expression. That's what we're going with. Okay, so what I want to do is I want to set myself up a little table. Okay, so let's keep in mind, we know that the gross area is 12.0 square inches. The I'll say DET is 0.875 square inches here, and then the stagger factor is 0.161 square inches. So again, this is why we do s squared over 4g times the thickness, so that the area comes out in square inches. So we're adding everything up consistently. Okay, so let's set ourselves up a little table. Here, I'll move this over a little bit so I got room. Okay, so let's look at our paths. So we had 3 paths. Let's look at path 1. Path 1, let's scroll up here. What did we name that? We named that ADF. Okay, so my apologies. I'm going to scroll a little bit more than I would like here. We have BCDF, ADEG, and BCDEG. Here, I got room. There we go. So these were the 3 paths that we defined. Okay, let's take each one of these paths and let's start identifying a couple things. So let's look at the number of holes, and then let's look at the number of stagger factors that we're going to need. Okay, so let's take a look at this. All right, so if we look at the number of holes, I think that's pretty easy. So our first path, ADF, how many holes are we subtracting? Well, we're subtracting 1 from the first one. Let's see, 1, 2 from the second one, and 3 from the third. That last path has 3 bolts. That's pretty easy. 1, 2, 3. Okay? Then the next question is, how many diagonal paths do we have along each of these paths? So let's go up here. So let's look at the diagonals. Path ADF is straight down. Path ADF is from top to bottom, straight down. So there are no diagonals at all. BCDF or ADEG, we have 1. And then the last one, BCDEG, we have 2 because we go down and then down. So a diagonal and then a diagonal. So 0, 1, 2. Okay, so for each of these rows, what I'm going to do is I'm going to compute a net area. So let's see how that works. Let's start off with the first one. So what's our formula? What are we doing? We're using this right here. Okay, so how does that work? Well, we take 12.0 square inches, which is our gross area, minus 1 times 0.875. So that's the number of bolts that we would be subtracting, plus 0.161. See that? And then the next one is 12.0 minus 2 holes, plus 1 stagger factor. 12 minus 3. And there we go. So let's see what we get. Let's just check these out. I'll scroll that up a little bit. Okay. So 12 minus... Okay, so here I'm getting 10.125. Oh, wait, sorry. Nope, that's... Yep, that's type. That should be 11. Okay. All right, so next one. I'm getting 10.411. And then the last one. $9.696. Okay, so here are our 3 answers, but wait a minute. let's take a step back. What the problem asked? The problem said, compute the net area. I got 3 net areas. Which one do I use? Well, let's talk about that. So what we've done is we have investigated and computed values for all of the potential failure paths that could occur. So if we, so what I'm saying is, if the failure occurs along path 1, we have an area. If the path failure occurs along path 2, we have an area, etc. So if the question is what's the net area, really the question is which way is this going to fail? Okay, and so conceptualize this. Imagine you're taking the piece of steel and you're yanking on it. It's going to fracture under the path of least resistance. Like we've all heard that term, path of least resistance. What that means is that it's going to fracture whenever its capacity is weakest. Okay, and how do we know when its capacity is weakest? We know when the capacity is the lowest, when the area is the smallest. In other words, it's easier to break through 9.696 square inches of steel than it is through 11.125 square inches of steel. So if I apply tension, it's going to fail on this lowest area first. Okay, and so we have a name for that. We call that the path that governs. Okay, so if you ever hear that term governing in structural engineering, it tends to mean either the lowest capacity, or on the flip side, it could mean the highest load. Whatever load combination yields the highest number. So if you remember the very first homework assignment, I had you go through a bunch of load combinations and you reported the highest value. The highest value governed on the load side, just as on the capacity side, the lowest value governs. So what is the answer? The answer is that therefore the net area is 9.696 square inches. That is the answer. Okay, so that's the answer. Hopefully that should be pretty straightforward. I'm going to go through a couple of things just from a logistics standpoint. So let me do that. First thing I want to show you is the upcoming homework assignment. So this is the upcoming homework assignment. So a couple things about it. I want you to compute the net area for this plate shown. There's a little bit more going on in terms of letters and potential paths and whatnot. The first thing I'll mention is that I went ahead and applied letters, the naming letters, the A, B, C, D, and what have you. I went ahead and did that myself because that way when we're grading and when we're all discussing it or what have you, that we're all referencing the same naming scheme, like path, whatever path name. I know path ABC is not an option, but if I say ABC and you say ABC, we're all saying the same thing, okay? So I want you to determine the net area of this plate shown. You've got the bolt diameters, all the dimensions here. Really the main thing that I'm looking for in this assignment is, beyond the right answer, is if you identify all potential paths, because there are quite a few of them. There are quite a few potential paths, but as you start investigating all of them and identifying them, you will see a pattern and it will be clear which one is going to govern. So I'm going to leave it with that. Now I do want to at least briefly mention what's going on in the next lecture, just to sort of set the stage for it, especially given the fact that if we start missing more school because of weather, I want to try and get a little bit more covered on that stuff. So I kind of want to at least talk about Lecture 6. So Lecture 6 is going to be primarily focused on shear lag and what's called a slenderness limitation. I'm going to turn my little heater off here. My office is getting a little toasty, so I wanted to turn that off. Let's go back to our basic discussion of limit states. So if you remember, what we're really doing is comparing loads and resistances. Now, we've already talked about loads and how to factor them. And in the not too distant future, so the way I'm teaching tension members is I'm going through each of the individual pieces regarding tension members. And then when it's all said and done, we're going to do full-blown start to finish tension member analyses and tension member design. So we're handling each little part. We'll bring it all together in the not too distant future, probably bringing it together on Wednesday when we start doing full-blown analyses. But just to make sure we're all on the same page, on the load side, we use our load combinations like 1.4 dead, 1.2 dead plus 1.6 live to get factored loads. And then on the resistance side, we take nominal resistances and we adjust them by these LRFD resistance factors. And as long as the factored resistances are greater than or equal to the factored loads, we're good. The structure's safe. Now for a tension member, we've been talking about gross section yielding and net section fracture. And really so far what we've been focused on is that for each of these sections, computing the gross area and the net area respectively. And I think between the last lecture and this lecture, computing gross and net area should be pretty straightforward, okay? So what does that mean in terms of the limit states? Well, for gross section yielding, the nominal capacity is the yield stress times the gross area. And the spec tells us that our resistance factor is 0.9. And our resistance factor for fracture is 0.75. And just so you're aware, the reason that the resistance factor is a little lower is because fracture is a little bit more dangerous. I mean, if a member yields, it develops permanent deformations. That sucks, but that's not the same thing as a member fracturing and actually separating. That's a little bit more dangerous, so we drop the capacity a little bit more. Now, for tensile rupture, we have the ultimate tensile stress F sub U times AE. And what is AE? Well, AE is the net area adjusted by a shear lag factor. So what does all that mean? So if I take this and I combine everything into one big old slide, so we have our factored loads, which we know how to do load combinations already, so we can look at factored loads. And on factored resistances, here's what we have. We have gross section yielding. And to compute the factored resistance, it's 0.9 times the yield stress times the gross area, which is pretty easy. If you know the gross area and you know the yield stress, just plug it in. So what about net section fracture? Well, it's 0.75 times FU times the net area times this term U, okay? If you look at this slide, we've covered everything on this slide, even FY and FU, because we learned how to look that up for different steel grades. So the only thing we haven't talked about is U. That's the only thing we haven't talked about is shear lag. So let's talk about shear lag, okay? Shear lag is a phenomenon that relates to disturbances in stress profiles around the connection. And that's a mouthful, okay? But I'm going to show you some very pretty pictures here in a second. So the idea behind shear lag is what's going on really on this slide. This is taken from some research that was done at West Virginia University. This was some captures from actually, it was my PhD advisor, is one of his master's students looking at shear lag for members with connection eccentricity. But just to state this very easily, so whenever we're looking at connections, we often don't connect all of the cross-section components. And that might be an odd thing to say, but the easiest way to describe what's going on is looking at the image on the bottom left. So the image on the bottom left is an I shape or W section connected via the flanges. So you can see we've got bolt holes in the flange. Here's a bolt hole, bolt holes. But the big thing is, what about the web? There are no bolts going through the web, so we have not connected all of the cross-section components. We've only connected some of them, okay? Now, what happens whenever you have these situations where not all components are connected, or really in general, whenever you have members with bolts and holes through them, if you actually look at the stresses they can get kind of weird. So this is the result of a finite element analysis looking at connection eccentricity, or looking at this phenomenon called shear lag. And I'll get to why we call it shear lag here in a second. But what's going on is that if you actually look at the gross section being sort of the main body of the member, the stresses are very uniform. And so what we're looking at here is the variation of stresses in the member as we yank on it. And out in the main body of the member, the gross section, the stresses are very uniform. You can tell that because the contour is yellow, Okay, it's all one color. The difference in colors on these plots here represent the changing of stresses, how much the stress changes from one region to another. So like you might find blue regions have very low stresses, and then red regions have very high stresses, and what have you. But we're not looking at the gross section. So if we go back to our equation, we don't have a U value right here. We're not looking at that in the gross section. We're looking at the net section. So when we look at the net section, the stresses are very non-uniform. They're all over the place, okay? And unfortunately, we can't ignore that. We have to do something about it. We have to account for that in some fashion, okay? Now, the reason that we call this phenomenon shear lag is because if we look at a situation like this, where we have some of the cross-section components connected and some of them not, what happens is as you yank on this member, you are directly applying load to the flanges, but the web's not seeing that load directly right there at the connection. It takes a while for those stresses to propagate from the flanges throughout the rest of the member. It takes a little bit of time, a little bit of distance along the member to do that. So what's happening is some of the member or some of the cross section is experiencing this yanking, this tensile force, and some of it isn't. Some of it is kind of lagging behind. It's waiting to receive that load. So you've got one member going, experiencing load like this, the other's not doing it, and so it creates an internal shear. That's why we call this shear lag. Okay. Now, if you want to accurately capture shear lag, you need to do some hardcore computational modeling. I mean, this can be kind of tough to do. But if you actually want to accurately want to capture it, that's what you got to do. Finite element modeling can take a long time to do. It's time intensive, and the more hours you put into it, the more money it's going to cost. So the question is, though, as I mentioned earlier, we can't ignore it. Like, it's happening. We have to deal with it. So how do we handle that? Well, designers use a more practical approach, and they use empirical expressions. So I haven't quite defined this explicitly, but this is a good time to do it. So we as engineers tend to use two types of classes of equations whenever we do analysis, do design, do what have you. One of those is what I'll call mechanistic equations. And mechanistic equations would essentially be anything that you could derive. You take some laws of physics, throw some statics together, throw a method of virtual work, and boom, you can compute formulas for beam deflections. Or, can you compute pressures and fluids for given situations using Bernoulli's equation? You can compute some pretty closed form expressions for that. Mechanistic equations, while valuable, they tend to be based on assumptions. And sometimes those assumptions break down. A good example is this right here. Sigma equals P over A is great, but we're assuming a uniform stress distribution. That is not happening here. This stress distribution is a mess, okay? So we need to be able to handle that. And that's where an empirical expression comes in. Empirical expressions are essentially what happens when you take a bunch of these members, you go down to the lab and you yank on them and you break them, and you collect all that data and you try and curve fit some expressions that best fits that data as closely as possible. Usually those expressions, and the really good ones, have some sort of theoretical underpinning to them, but you do, they are empirical in the sense that they're not 100% going to accurately capture the effect, but they do capture it good enough to be able to design, good enough to be able to account for that from an analytical perspective. So I would say that folks who are doing the finite element modeling that we see here are either designing something that's really complicated where the equations aren't going to work, and unfortunately this is a problem and they need to deal with it, or they're doing research, which, I mean, we do need to be able to do that in that setting. But for most practical engineers, they're not going to do that. They're going to use an empirical expression, and that's where the code comes in. The code has very simple provisions. I'm moving my camera again, my apologies. The code has very simple provisions for the ability to compute shear lag factors. So what is a shear lag factor? In short, we have the net area, and what we're asking is, of that net area, how much of that net area is effective in resisting load. And so we take that net area and we reduce it a bit to account for this shear lag phenomenon. And that's what shear lag factors are doing. And so if you open up the spec, there is a catalog of shear lag factors that are dependent upon what type of members being connected, what is the connection scenario, etc. I don't want to get full bore into this today. We're running short on time. We're hitting our 50-minute mark, so I don't want to get into this today. I just want to present the idea. When we come back on Monday, we're going to take it from here, and we're going to assess what are shear lag factors, how do we compute them, how do we assess them, and we're going to have a homework assignment just on that, just on computing shear lag. But there's another part of this lecture that we're not talking about, and that is slenderness. So in this lecture, we're going to discuss not only shear lag factors, but what happens when members get too slender, or more specifically, what is slenderness, and how do we define it, and how do we limit it for tension members. But I will save that for next week. That is all I have, everybody. I will see you all on Monday. Please stay safe, stay warm, and have a good weekend.